Okay, so I'm very pleased to introduce Mark Srednicki, who will tell us about quantum mechanics on the adele class group.
Thank you very much. It's a great pleasure and an honor for me to be here. Many thanks to the organizers for the invitation. It's been a wonderful meeting so far. I've been fascinated by number theory ever since I was a boy. I remember when I must have been 12 years old or so, going to the public library in Akron, Ohio, and checking out books with titles like The Lore of Large Numbers. Since then, I lost my way and became a physicist, but now it's an honor to be able to speak to you on the topic on which you are all the experts. I have to start with a slight clarification. If you look at the little booklet of abstracts, the computer on which those were prepared did not like my accent grave on the E and deleted not only the accent grave but the entire E. And so I want to clarify that I will not be talking about The Idle Class, which is a 1921 movie by Charlie Chaplin. All right. What I will be talking about is something that I think essentially all physicists, certainly including me, are fascinated by, which is what is now usually called the Hilbert-Polya conjecture, that the imaginary parts of the zeta zeros are the eigenvalues of some self-adjoint operator. And it's kind of interesting, I think, to ask why physicists are so fascinated by this. Usually, we don't much care how mathematicians prove something, but we think we know a lot about self-adjoint operators because we use them all the time. In discussing physical systems, usually the way we talk about them is by writing down the Hamiltonian operator, whose physical, it has two very important physical significances. One is that its first physical significance is that it's the total energy of the system, and its second, at least as important physical significance is that it controls the time evolution of the system. And so we're very good collectively at constructing operators that have certain properties. And so when you tell us, oh, I've got this list of numbers and I want them to be eigenvalues, we think, sure, we'll just do it. Of course, those of us who actually try quickly find out it's much harder than that. But I'm going to tell you about my personal attempts to understand this problem and to hopefully, my goal is to make the tiniest possible contribution, which is to possibly suggest an idea which might possibly be useful in the real problem. So first I'm going to tell you about quantum mechanics, and in particular quantum mechanics on the real numbers. Most of the time, to construct our systems, we have two operators, x and p. X represents the position of a particle, here just on a real number line, and p the momentum. And famously, these don't commute, or fail to commute. Their commutator is I times a number called h bar. If you're an experimental physicist, h bar is approximately 10 to the minus 34 joule seconds. If you're a theoretical physicist, h bar is 1. And if you're a number theorist, h bar is 1 over 2 pi. So I will use the number theory convention. And I will use this Dirac-Bra-Ket notation, in which the thing with the angle brackets is an eigenstate. The x here is an eigenstate of the position operator with eigenvalue x. The p is an eigenstate of the momentum operator. And I will ignore the fact that these things don't actually exist, because another thing physicists are good at is being comfortable with ambiguity and imprecision. And the hope is that this can actually be useful sometimes in possibly allowing us to look into areas where the imprecision can eventually be cleared up and made mathematically precise. The inner product of x and p looks like this. And you can see that this, if you're a number theorist, this probably looks like an additive caricature, additive character to you, and that's why I call this the number theorist convention for these things. By far the most important physical system is the harmonic oscillator, which can be said to be specified by having a Hamiltonian which is x squared plus p squared. If we were doing physics, we would put different coefficients in front of them. I'm going to call both coefficients 1/2 omega naught, and omega naught will actually be 2 pi. None of that is going to matter. This operator has discrete eigenvalues, conveniently labeled by a non-negative integer, and the actual value is shifted by 1/2. This is a famous problem that's in every undergraduate quantum mechanics textbook and done a number of different ways. It's the starting point for virtually all physics problems that we can actually solve. We heard Ralmar Vulkankar talk about a particular quantum field theory, and he put up a famous formula, the formula for the magnetic moment of the electron as a power series in the electron charge, where it's possible to calculate the coefficients in this series, each coefficient requiring an order of magnitude more labor at least to calculate, but the first 4 or so are known. And that gives you the predicted numerical value of the magnetic moment of the electron to 13 significant digits, and it can also be measured to 13 significant digits, and those numbers agree. By at least some set of criteria, this is the most precisely predicted and measured quantity known to humanity. But the starting point for those calculations is a bunch of harmonic oscillators. So, very important problem in physics. We also can specify the eigenfunctions or eigenvectors by giving them in the position basis in this notation. There's some Hermite polynomials times a Gaussian. In 1999, Michael Berry and John Keating introduced something that I like to call the sideways oscillator. The Berry-Keating Hamiltonian is XP. This appears in many different contexts. We heard Herman Verlinde this morning. We talk about this operator appearing in the context of conformal field theory, where it's more often called the dilatation operator. Michael and John, in 2 very nice papers, suggested that there are some interesting connections between this operator and the Riemann zeta function. And I won't try to review all the connections that they found. I'm just going to take that as a given that this is going to be an interesting starting point. And again, in the usual physicist imprecise way of not caring very much exactly what space these things live in, we can say that the eigenvalues of the Berry-Keating operator are any real number, and I'm going to call that number E for energy, and it's any real number. And there's also a second discrete label pi, which we can say what that means by looking at the eigenfunctions. The eigenfunctions have this form: the absolute value of absolute value of x to a power I'm going to call s minus 1. I'm going to freely move back and forth between s and e. E in Riemann notation is height up the critical line. Here there's an unfortunate mismatch between math and physics. Of course, in math, you like to call this t. From a physics point of view, that's an unfortunate choice of letter, because t to a physicist means time, and we want it to be energy. So here I'm going to follow the physicist convention and call this E. But I'll sometimes talk about E and sometimes talk about S and go back and forth. Pi is either 1 or the sine of x. which the number theorists will recognize as the unitary characters on the real numbers. Okay, now I want to talk about something called the local Riemann hypothesis, originally due to Bump and Ing in 1986, and Bump and these other folks follow up in 2000. And although it's called the local Riemann hypothesis, it's not actually a hypothesis, it's a theorem, which is not that hard to prove. And here it is in the notation I've introduced, which of course they weren't using. I take the inner product of a harmonic oscillator eigenstate with a Berry-Keating operator eigenstate. And if I do that, depending on what n is and what pi is, I might get something that's just exactly 0. Or I might get something that's not 0 and therefore is a function of e. The way I've defined e, it's real, but you'll get some function and you can continue that function into the complex e plane. And the statement of the local Riemann hypothesis for the reals is that if you do that, you will find that that analytically continued function, if it has any zeros, all those zeros will be at real values of e. Now, this is, I think this should be regarded as somewhat surprising. There's nothing in the general structure of quantum mechanics that tells you that if you take an inner product like this, you have to get something that can only have real zeros. And it's easy to construct counterexamples of other systems for which this doesn't work. There's also the mystery of why this has anything to do with the Riemann hypothesis, the real Riemann hypothesis, and why that might be the case. There's a hint for why that's the case if you actually compute this. So here I've computed the simplest one, the ground state of the harmonic oscillator with the Berry-Keating state with unit character here. And you get this factor, which all of you will recognize as the factor that you should multiply the zeta function by to get the completed zeta function that satisfies the simple functional equation. So this is something that shows up when you study the functional equation of the zeta function. And the statement of the local Riemann hypothesis is that if we, instead of using 0, use an excited state, and if I stick to the trivial character, I need to make this an even number, what I get is the same factor and now times a polynomial, which you can think of as either a polynomial in E or S. It's a polynomial in either variable. And the statement is that this polynomial has only real zero, expressed as a polynomial in E, has only real zeros. And this is not hard to prove. It's a finite polynomial. We know lots of stuff about finite polynomials and can prove it has real zeros in several ways. The other case is where we use the sign character on the right. Then we need an odd number on the left. And now you get something else as the prefactor. You get something that you'll recognize as the completing factor for Dirichlet L functions with odd characters. And again, for n not equal to 0, you get a polynomial. And again, that polynomial has only real zeros. And I think it's interesting to ask, why, is there a reason why this polynomial only wants to have real zero? And a couple of years ago, I noticed something about this polynomial that I think of as a reason why it has only real zeros, which is that you can write it as a spectral determinant. I take the Berry-Keating operator and subtract E, and then I take its matrix element between harmonic oscillator eigenstates. And I'm going to restrict how many states I use. I'm only going to use states that are below the label that sits on the left here. And if I do that, I restrict the states, and I take the determinant within that subspace, I get this object. So once I'm not going to prove this. It's a few-line proof to show that these two things are the same. But once you show that, it becomes immediately obvious that it can only have real zeros because this is now the spectral determinant of a self-adjoint operator.
Where does pi show up on the right-hand side?
Pi shows up in that if pi is 1, I should only use even numbers on the right, and if pi is sine, I should only use odd numbers on the right. Yeah. So I think this is quite nice. This is what we would like to do for the real Riemann hypothesis. We would like to find an operator, and here we have the operator that Berry and Keating suggested had something to do with the zeta function, and it's that operator in a restricted subspace that whose eigenvalues are the zeros of this factor. Okay, and yes, the goal is to apply this to the actual Riemann hypothesis. I think it will not surprise anyone if I say in advance that I am not quite able to do that. But that's the goal, and my goal is to take a tiny, tiny step towards this true goal. Yeah?
Can you show us what these energies look like when n is large? Anything like the Riemann zeros?
No. Well, first of all, there are only a finite number of them.
When n is large?
Yeah, yeah. What they do, prompted by prior communications with you, I did compute that. And what they do is they tend to fill in the density. So the real Riemann zeros have a density that's increasing logarithmically. These have a density that decreases logarithmically up to some cutoff. And if you put them together, it's uniform. Why that's true, I have no idea. All right. Now, again, if you know why the local Riemann hypothesis is called the local Riemann hypothesis, you will know that the next topic is going to be quantum mechanics on the p-adics, because we've done the reals. Now we have to do the p-adics. This morning, Phil Candilos told us what the p-adics are. For those who don't know, I'm not going to try to explain that again. In the late 1980s, this suddenly became a topic of interest in physics for reasons I don't really know. Suddenly, several groups decided it would be interesting to see how much of physics could be generalized from real numbers to p-adic numbers. And let me tell you how this works. I said at the very beginning that the Hamiltonian is important because it also governs the time evolution of a quantum system. This is how it does it. This is true in general. If you know your Hamiltonian, you exponentiate it in this way with a factor of I and a factor of t, which represents time, and you get an operator u. If you know the state of the system at time 0 and you apply u to it, that's the state of the system at time t. Here I'm just going to do something a little weird notationally. Instead of thinking of this as labeled by t, which is the natural thing to do and the thing you'll see in every physics textbook, I'm going to think of it as being labeled by something I'll call a, which is just the exponential of t. So that's just a notational quirk that I'm going to apply here. And another way to tell you what an operator is to give you its matrix elements in some complete basis. So here I'm going to use a basis of position eigenstates. I should clarify that even though it says quantum mechanics on QP at the top, right now we're still doing quantum mechanics on R. I'll get to QP in a second. Right now all these formulas are on R. And you can easily show that this is what the matrix elements look like. This is the Dirac delta function. And similarly, we can do the harmonic oscillator. But again, I'm going to use a notational quirk where I'm going to talk about the cosine and sine of the time instead of the time itself. And again, you can write down matrix elements. This is some fourth or eighth, I can't remember, root of unity that comes in front. That depends on the parameters, but I won't say what it is. So this is a general formula. And now the punchline is that the red boxed equations all make sense if everything is a p-adic number. When I say everything, not the right. The right-hand side is a complex number, but x and y, the position eigenstate labels, and the parameter labels a, c, and s all take values in QP. And the norms that appear in a couple of places now denote the p-adic norm. Okay, and this is what these folks figured out in various ways. All right, well now I have, instead of a Hamiltonian, I have a time evolution operator. And I can ask about eigenstates of that just as well as the Hamiltonian itself. So let me ask about eigenstates of the very Keating time evolution operator. And they take this form. They're still labeled by a real number and by a character. But now this is any multiplicative character on the p-adics, which is, of course, a vastly richer and more complicated structure than on the reals, where it's trivial. And similarly, the energy eigenstates, I'm going to call these energy eigenstates. And I'm going to think of my parameter E, my real parameter, as an energy. And I'm still going to switch back and forth between S and E in the standard way. Has this form, the multiplicative character appears in front. The states of the harmonic oscillator are quite complicated. There are books devoted to talking about this. The only thing I will say about these states is about the so-called ground state, which is the simplest state. If on the reals, it's just the Gaussian that we're familiar with. On the p-adics, it's the indicator function on the p-adic integers. And why that's true, I'm not going to explain. Okay. And the major thing that we need to know is that the inner product of the harmonic oscillator ground state and the very Keating eigenstate with trivial character is this thing, which is, of course, the factor in the Euler product when we go to compute the zeta function. And there's a local Riemann hypothesis for QP for every p except 2. It's never been proved, as far as I know, for p equals 2. But for odd primes, it was proved by Kurlberg in 2000 in a companion paper to the Bump et al. Paper. And the statement is the same. If you now look at excited states of the harmonic oscillator and take its inner product with a very Keating state with some character, you might just get 0. But if you don't get 0, you'll get something that's a function of E that only has real 0. And in that paper of a few years ago, where I showed that that on the real numbers, you got this very nice result that this was a spectral determinant, I couldn't quite get it to work on the p-adics. So I still think it should be possible, but I couldn't quite get it to work.
Can you go back and tell us, so there is, you're talking about real zero, so there is a real variable that is a p-adic variable.
Yeah.
Okay, so where is our, maybe you should be able to tell us where these various things are, which ones are real, which ones are p-adic.
Okay. So we have a unitary operator, which I'm so the way you would... It operates on a complex function of a p-adic variable. Okay. So I would have a state that I would call psi. And this would be complex. And this would be p-adic. Okay. And then I would create I'm going to put a number 1 here. And so this is going to be like, roughly speaking, you should think of this as the exponential of time. And now I would write a formula like this. And this is for t equals 0. I would write a formula like this. where this integral is, so. Oh, and this should have been 1. Yeah. Yeah. P-adic integration. But yeah, thank you. That was good to clarify that. Okay, let's see. What do I have to press here? I think this works. Okay, and then in these eigenstates, so all this stuff is complex numbers, and this is the p-adic norm of A, which is p-adic, but of course the p-adic norm is itself a rational number. So the eigenvalues of this unitary operator are complex numbers on the unit circle. Okay, and then, yeah. Local Riemann for QP. The energy is real, but the energy is real sort of by definition, because I'm just declaring my operator to be unitary. And yeah, but really we should do it in a better space and be more careful. E and S, yes, that's E is T, but I won't call it T because that offends my physicist sensibilities too much. If only you guys had called it E, life would be so much easier. I guess we can blame this on Riemann. Yeah, I got rid of T too, so. Yeah, there's no T. T is gone. But you can't call it ET because it's just. OK. Now I'm going to talk about the things that the computer didn't like and wanted to delete my accent grav. I like to put the accent grav on because when I first started learning about these things, I was learning about them by reading them. And I was reading, whatever I was reading didn't have the accent, so I wanted to pronounce them adele and ideal. And I would go talk to mathematicians, and they would not understand what I was talking about. Anyway, so you guys all know this, but we have adeles, which Philip Candelas mentioned this morning, infinite component vectors in which the first component is a real number designated by this weird subscript infinity. The next number is a 2-adic number, a 3-adic number, and so on. We define a norm on these, which is an infinite product of the individual norms. Each is the norm appropriate to whatever kind of number we're taking the norm of. And we demand that the infinite product not be infinite. Principal adeles, also mentioned by Philip, are adeles where we take a rational number, Q, and we put the same rational number in every slot, which we're allowed to do because rational numbers are real and 2-adic and so on. And the norms are defined in such a way that the norm of this thing works out always, no matter what Q is, works out to be 1. Adeles, we demand that the norm not be 0. Most of these are going to come out 0 because you're multiplying a bunch of numbers together and probably going to get 0 if you don't do something to prevent that. And then the most interesting thing are the elements of the adele class group, which is what you get if you identify any 2 adeles that are the same up to multiplication by a principal adele, where the multiplication is done pointwise for each of the factors. And here I want to chide the mathematicians a little bit. This is a terrible name. These things really need a better name. Adele and adele are nice names, and you can't go around saying elements of the adele class group all the time. So I want to call these things the models. Sorry?
Your Q's are rational numbers.
Yes, Q is a rational number. Ordinary rational number. Which is why it's allowed to go in every slot. All right. Now, also about the same time that Michael and John suggested XP had something to do with this, Elaine Kahn took that up in a way and wrote a couple of papers that I find pretty much incomprehensible, but one of my motivations for doing this was to try to see what I could extract from those papers and just try to have some idea of what he was doing. And this is my interpretation of what he was doing, which is probably not at all what he was actually doing, but so anything that's wrong should be, which is probably most of it, should be blamed on me and not on him. I think of what he was doing as defining an operator that I'm going to call the Berry-Keating-Kahn-Hamiltonian, which, roughly speaking, we get by taking the Berry-Keating-Hamiltonian on the reals and replacing the real number x by the norm of an adele. And I'll be more precise by specifying the eigenvalues and eigenfunctions of this operator. So it will have eigenstates that are labeled by this real number e that I keep talking about, and also by a primitive Dirichlet character. And the eigenfunctions will be given by this factor, which keeps appearing all the time, now the adelic norm to the power IE. And in front will be the Hecke character that's derived from the primitive Dirichlet character by the Hecke recipe, where you get a character on each of the factors according to some prescription, each of them being derived in some way from chi. And then this has the property that it's invariant under multiplication by q. And so that clearly, and that's also true of the norm, so that extends to this whole wave function, as we would say in physics, which, okay, you don't like my term, I still like it, means that the configuration space that this thing lives on is really the models, the elements of the adele class group. Now, we can also take the harmonic oscillator, multiply them all together, and get an adelic oscillator, which we'll just get by now taking the infinite product of all these oscillator ground state wave functions. And here, remark parenthetically, the configuration space the x's live in, is really now the adeles, because there's nothing that's telling me I shouldn't have things of norm 0 in there. But now if we take the inner product of the ground state and the Berry-Keating-Kahn eigenstate with trivial character, we just get, by multiplying all those previous factors together, the completed zeta function. And so everything I've said is really just Tate's thesis, but I'm associating, to the extent that there's anything new, the thing that's new is the words I want to say about what's on the left-hand side. So if we actually wrote this out as an integral, it would just be Tate's global integral that gives you this. But I want to think, for Tate, the harmonic oscillator eigenfunctions were just some test functions that happened to give what he wanted to get. And the Berry-Keating eigenfunction was taking the Mellin transform. So I want to think of these things now as a quantum mechanical inner product between a state that has some independent meaning, namely it's the ground state of this adelic oscillator, and the Mellin transform is not just some transform we pulled out, it's an eigenstate of this other operator, the Berry-Keating-Kahn operator. And similarly, if we fiddle around with some of these factors, and bump them up to some low-lying excited states of each individual oscillator, we can then get non-zero inner products with other Dirichlet characters over here and construct the completed L function. And again, usually you don't need to do very much. So on the real case, for example, for the real factor, you either use the ground state, which is just the Gaussian, or you use the first excited state, which is just x times the Gaussian. That's what you need for the odd characters. And then you don't need the rest. The rest come into the local Riemann hypothesis, which says that if you felt like using those, you will generate some extra zeros, but those will also be on the line. Now, a problem is the right-hand side, the Berry-Keating side, which has the Hecke character. That's really nice, right? That's got all the nice stuff in it. The left-hand side, the adelic oscillator, that's not so nice. We would like to make that nicer by projecting it onto the nice things, which are the models. And Kahn, you can find this in his paper. This prefactor doesn't really do anything. This basically, you have to decide whether you're using the additive measure or the multiplicative measure. And if you're talking about the adels or the models, you should be using the multiplicative measure. And so this converts the additive to the multiplicative. And then we just have this brute force sum over all the rationals. That's not very nice, or at least I don't know how to think of it in a nice way. And the other problem with it is, if you do this, you can do this to every one of these states, but if you do it, they won't be eigenstates of the adelic harmonic oscillator anymore. And in general, they won't be orthogonal, because they're not eigenstates of some nice operator. So what I think we should do is find the nice version of the harmonic oscillator on the adele class group. I think if we knew what the harmonic oscillator on the adele class group was, that would tell us a lot. And then, and of course, I have no idea how to do this. That would be step one. Step two would be to rerun the proof of the local Riemann hypothesis, which now should hopefully work in a nice way, because you know what these nice states are, and it will all work out. OK. And that's really what I have to say, mostly. Almost all. The rest of this is going to be some comments on Katz-Sarnak families. But that's my ill-defined program for a physicist way to prove the Riemann hypothesis. We have the right-hand side, which is really nice, and a left-hand side, which is not so nice. And I think if we could find a nice left-hand side, it would tell us something. OK. And of course, I can't do that because I don't understand this stuff anywhere near well enough to do it. But hopefully, some of you can do it. All right. Now I want to make some comments on Katz-Sarnak families, and in particular, the family that includes the zeta function. According to their way of thinking about this, if you look at Dirichlet L functions with even real characters, you should get some sort of family that has some sort of symplectic symmetry. In the physics literature, we have the Altland-Zirnbauer classification of random matrices. There are the original 3 Dyson matrices, which are over here, and then there are 7 more. And these are classified according to how they behave under time reversal, charge conjugation, assuming we have some sort of charge to conjugate, and S is some sort of product of T and C. I don't really want to explain any of this. The main thing, just phenomenologically, is we know we need to get quadratic repulsion of zeros everywhere on the line. That corresponds to beta equals 2. And for this family, we expect repulsion away from the 0 point on the axis, again quadratically. And that uniquely tells us that we're supposed to be in class C of random matrices. Now, if you're actually trying to find an operator whose eigenvalues are the Riemann zeros, that means it should live in class C. And Altman and Zirnbauer describe how you actually construct physical systems that live in one class or another, depending on how it behaves under these particular symmetries. So a class C Hamiltonian, here I'm writing it as a matrix in some basis. So we imagine we have some nice basis that we know how to deal with. And then the Hamiltonian in that basis takes the following form. There's a particular two-value degree of freedom. These are, for physicists, these are Pauli matrices. For mathematicians, they're generators of SU2. So there's an SU2 spin that's picked out as special. And we have random matrices that are antisymmetric. One random matrix that's antisymmetric times the identity operator in this SU2 space. And 3 that get multiplied by the, oops, that's supposed to be Kj. I think this is a little too obvious with Jk. No one will disagree with that. Yeah, this is supposed to be symmetric. OK, so that's the structure. So if you're going to try to look for a Riemann Hamiltonian and you're going to restrict to real even L functions, it should look like that. But how does that match up with everything I said before about it being the very Keating operator? I have no idea. But if this worked, that's another natural question that should fall out of the correct way to do this, assuming it could work at all. I do want to make one more comment about this, though, which is some formulas for the density. I'll call them eigenvalues. These would be, for the Riemann, these would be the densities of zeros. And this is the oscillating part, what Michael in his talk called the fluctuating part. There's a constant, well, not a smooth term that gets added to this. And Michael and John wrote a number of papers about the analogies between this formula for the Riemann zero density and the eigenvalues, the energy eigenvalues in a chaotic system. There are many similarities, but one important apparent difference is minus signs. Here we have an overall minus sign. Here we have a plus sign. But we also get some phases called Maslov phases that we can play around with. But you can't ever get an overall minus sign. Nevertheless, it turns out that chaotic systems in class C are special in a certain way, as pointed out by Nutzman et al. They have a particular structure of Maslov phases. Basically, they're all pi, which then gives you a -1 to the r here. R is the number of repetitions. So this is still not the same, but it's a lot better. In general, if you wrote down some chaotic system, these Maslov phases generally like to be 0. So you're probably going to have a sign mismatch. Here you're going to get the primitive, so-called primitive orbits contribute with the minus sign that we want to match Riemann. And then repetitions, that's what R stands for, repetition. The orbits get repeated. The repetitions even repetitions have the wrong sign. But those are usually subdominant in some sense. So maybe you can get it to work. And in the paper I wrote on this, I concocted a toy model where there were some cancellations between primitives and repetitions in such a way that at the end of the day, you got just an overall minus sign. So it's at least mathematically possible for that to happen. And the reason I want to make a point about this is because this minus sign was very important to Kahn in his paper. He wanted to argue that this minus sign meant that the Riemann zeros should not be discrete eigenvalues, that they should be missing eigenvalues in a continuum. And us physicists never could quite understand, I think, how that was going to work or how that was going to help. But I think what this class C business shows is that you don't need that interpretation. You get enough minus signs in class C that you can probably live with this and still have them be what physicists would like them to be, which are discrete eigenvalues of an operator. All right. Oh, and now I've circled all the minus signs. OK, I'm done. What are my main points? Structures related to the Riemann hypothesis appear naturally in quantum mechanics on the Adele class group. The example of the local Riemann hypothesis on the reals, at least, and maybe on the p-adics, suggests that understanding the harmonic oscillator on this space would be a good thing to do. And maybe you know some mathematical structure that corresponds to that I haven't heard of. That would be great. But as far as I know, nobody knows what this is. And somewhat sub-point, if you're going to understand, if there is an operator that corresponds specifically to L functions with even real characters, including zeta, it should be in Altman-Zernbauer class C, which is the same as the Katz-Sarnak symplectic family. And I don't understand how this intersects with this, but if it all ever works, it has to intersect in some nice way. So thanks again to the organizers for a wonderful meeting.